share my screen here. Can you see my screen?
Yes, it's fine.
Okay. Are the slides passing?
Not really. We can only see the first one.
Oh. That's weird because it was passing slides.
Did you share your whole screen or just a window, maybe?
I'll try again. Just a second. Okay, are the slides passing now?
Yes, it's fine.
Okay. So I will start. Good morning, everyone. Thank you so much for the organizers for the opportunity to participate in the workshop. And I really would like to be there in person. I hope one day I visit you in Natal. And also, I apologize because I think this presentation will be a bit more theoretical than the previous ones. So please feel free to interrupt me at any point if you think things are not clear. So yeah. So this presentation is about a mathematical tool to construct effective field theories. So it's a very agnostic approach. So some people say it's called a bottom-up approach, and I will focus in particularly on a scenario where we extend the standard model with an additional particle, a singlet, which is neutral under the gauge groups, and it's a higher spin singlet, so potentially a higher spin dark matter particle. And so yeah, so why should we care about effective operators? Why are they called effective? Because all physical theories, in some sense, they are effective field theories because before, for example, constructing a Lagrangian for a theory, we have to choose which degrees of freedom we are going to neglect and which we are going to really consider to do the physics. So it is always effective in some sense because we're always neglecting heavier modes, like heavier fields, if you want. And the way you for example, you can parameterize your ignorance is by means of those effective operators. They constitute higher dimensional operators. So your Lagrangian density your main part of Lagrangian density is composed of up to dimension 4 terms, mass dimension 4. And if we start including higher dimensional operators with coefficients, dimensionless coefficients, which are those CJs here, we can parameterize our ignorance by trying to find deviations from zero. So if we measure something that points that those coefficients of the higher dimensional operators are different from zero, it will be a clear sign of new physics. So this is a bottom-up approach because instead of starting from a UV complete theory, we start from the like the main part of the Lagrangian and build the operators out of it, and then you can do the matching with the UV completion. So this is another way to try to search for beyond standard model physics. Okay, but some examples of these effective field theories is, for example, I think the most famous one is the Fermi's theory of electric interactions. It's you include a 4 fermion operator, and from that you could search for deviations of these coefficients, and after 30 years from the publication of the Fermi's theory of weak interactions, which was in, I think, 1934, Weinberg published the Weinberg and Salam, they published the paper unifying the electroweak interactions. So on top of these deviations, it's possible to search for a more guided search for UV completions. And so as you can see, there are several examples. You can do effective field theories with gravity, for example. You can take the Einstein-Hilbert action and start including higher dimensional terms in which are composed of the Ricci tensor, and you can always try to parameterize your ignorance in this way. And as you go to higher energies, heavier fields may start to take into play. And if you go to lower energies, you can integrate out your heavy modes and and work with a low energy effective field theory. So that's more or less how this approach works. Okay. And in the case, so let's go to the specific case of the standard model. We can kind of follow a recipe to build an effective field theory with the standard model, because it's the standard model is currently the most well experimentally tested quantum field theory we have. And the recipe is that you basically have your gauge groups and your Lorentz group, and you have a series of fields, some fields, and those fields, they have charges under which they transform according to these groups. Okay, so this is like the list of fields that you have in the high energy standard model, so before the Higgs mechanism. And you start with this L0 here, which is the main standard model Lagrangian, and you can add higher dimensional operators, which are composed of those fields. Okay, and so the dimension 4 terms we are all familiar with, but then we can ask ourselves, what are the higher dimensional terms? And I mean, you can always try to do a brute force calculation. So you take all possible combinations of fields which respect your symmetries, and see which ones you can write and how do you contract your indices. And Weinberg was the first one, as far as I know, to do this, and he only found one operator at dimension 5, which is called the Weinberg operator. And it's funny because it's the leading order higher dimension operator, and you can give mass to Majorana neutrinos like this using this higher dimension operator. And you can also go to the yes.
Sorry to interrupt. Can you remove this note on Google Meet?
Oh, I'm sorry. I thought it was only showing for me.
No, sorry. Okay.
I apologize. Should I go back some slides? Okay, I don't think it was. Okay, I will continue from here. Okay, so after dimension 5, you can go to dimension 6, effective operators, and there's a lot of them, a lot of operators. So if you only consider one fermion generation, there are 84 operators, and it took a while for people to arrive in this basis, because the first attempt to construct this dimension 6 basis was by Buchmer and Weiler in 86, and actually they found more operators, so more, they found 80 operators, but their basis was neither complete nor independent. So there were operators missing, and many of the operators they showed were actually redundant between themselves. So you could perform, for example, field redefinitions, or they were linearly dependent, so you could make a change of variables and rewrite one operator in terms of the other. So this is a really hard problem to choose which operators you're going to work with without being redundant. Why is this even dangerous? Because if you forget to include some operator in the effective field theory basis, you might not be able to capture some beyond standard model physics. So suppose that some Wilson coefficient should be non-zero. If the operator corresponding to that Wilson coefficient is missing, you will never be able to capture the UV physics using the EFT approach. And on the other hand, if you include operators which are redundant, you will have non-physical Wilson coefficients. So, for example, if you do a global fit, you may undergo overfitting issues, and which are completely non-physical. So you have to get rid of those redundancies. And I mentioned here two types of redundancies. The first one is the equation of motion redundancy, and the integration by parts redundancy. The equations of motions are relations that you can express. You can you can relate two operators by using this transformation here, employing equations of motion. And the other is the integration by parts, which is the following. Analogous in analogy with classical mechanics, for example, where the Hamiltonian or the Lagrangian is not unique up to a total derivative on time. The Lagrangian density is not unique also up to a total derivative and the space-time coordinates. So you should also always be able to do these filter definitions and get rid of those total derivatives because they are non-physical. Okay, so what is the systematic approach to tackle this problem, which is very non-trivial? We don't want to do this by brute force calculations to high orders, right? So you can start by considering that the fields of your Lagrangian, they transform under group irreducible representations. You have Lorentz groups and cage groups. Sorry, the Lorentz group and cage groups. And the fields, they transform under irreducible representations of them. And in general, you can always take tensor products of your representations and then decompose them. And after this decomposition, what do you want? You want to select only the singlet parts, the vector spaces that remain invariant after these transformations. So in your Lagrangian, you want terms that are invariant under those symmetry groups. And how do you systematically select singlets? So there's a technique which is called Haar integration. So you can usually you can perform integrals along a straight line or a plane or a volume surface, but it turns out if your symmetry group is compact, you can also perform the integral along the group. So you parameterize the elements of your group, and then you perform the integral in your group. And this integral is called Haar integral. And it has a Haar measure, so it's a bit more technical, but if you want, I can explain better later. And the integrand of this integral is the character of the representation. So what is the character? The character is basically the sum of the eigenvalues of the representation. So the fields, they transform under representations, okay? These representations, you can express them as matrices, and after you find their eigenvalues and sum over them, you will find the character. Okay, so the integration is along the group, and the character is also a function of the group elements. So when you perform this integral, it turns out you can select singlets. And this is a beautiful and well-known result in mathematics. But people realize that you can use that to physics and to construct EFT bases. And pretty efficiently, by the way. So the question is now turned to construct this big character, the character of the operators that you want. Okay, so remember when I said that we want the basis to be complete, to describe all possible UV completions. So we don't want to miss any operator. Okay, so this big representation whose character we are integrating along, this big representation has to be the most general possible. So notice that our operators, they're always product of fields and derivatives, okay? Actually, derivatives applying to those fields, but always products. There are always products of those fields and derivatives. So what you can do is to try to construct the representation of the powers of the tensor powers of those representations of each field, because it is not just a tensor power. You have to take the symmetric part or anti-symmetric part depending if the field is bosonic or fermionic, because you don't want to write an operator that vanishes identically after you perform like commutations or anti-commutations. So to ensure that you will not have non-physical characters, you have to take this. You have to be careful with this. And there's also already a tool in mathematics that does that for us, which is called the platistic exponential, represented by this PE here. And everything you put in this PE, this platistic exponential, it gives you all the possible symmetric and antisymmetric combinations. So what we're going to do is that we are going to put the characters of the fields in those platistic exponentials, and then we are going to integrate them over the Haar measure to get all the possible consistent fields, to consistent operators in the EFT, okay? And there's a final formula for this, which is called the Mollin-Weil formula, which is just a projection over the subspace of allowed terms in the Lagrangian, basically. So you see here that there's a Haar integral for the gauge groups, another Haar integral for the Lorentz groups. You have the platistic exponentials here to generate all the big representations. And then there's this funny little 1/p here that is a factor that correctly addresses integration by parts. So imagine that to every field that you have, you can always apply an infinite tower of derivatives on it, and you don't want like an infinite tower of derivatives. So this 1/p takes into account this integration by part redundancy that you have for each field, okay? And after you expand this formula, you can expand it around around 0, and you get a series. And this is called the Hilbert series, okay? So how do you interpret this series? These coefficients here tell you that there are this number of operators which contain n derivatives in R1 fields phi 1 up to Rn fields phi n. So this is how you interpret this series. And in the end of the presentation, I think it will be more clear that it will show like explicit results on how to do that. So how to address equations of motion now? We showed how to address integration by parts. The equations of motions, they are a bit different for the cases of massless fields or massive fields. For massless fields, you can, since them already transform under Lorentz irreducible representations, you can just attach a scaling dimension to them, which is greater or equal than a certain number, which is called the unitarity bound. And then it will be an irreducible conformal representation. And there's another beautiful result that tells you that when this scaling dimension saturates the unitarity bound, you get new states in your representation, and those new states, they correspond exactly to equations of motion. So that's the recipe for massless fields. It's very easy. You take a massless field which transforms into some Lorentz irreducible representation. You assign a scaling dimension to it, like really artificially. It doesn't have a true physical meaning. And then you impose that this scaling dimension equals to the unitarity bound, and this has a one-to-one correspondence to equations of motion. And this is just to show you how the conformal generators they act. The K mu is the special conformal transformations, and the P mu is the translation generator. And every time you apply a translation, you jump from a primary to a descendant, and so on and so forth. Okay, and the primaries are the only one which don't have total derivatives. And for massive fields,
Bruno, you
Yeah.
have 4 minutes.
Okay, thank you. For massive fields, the situation is a bit different because massive fields they cannot they do not respect conformal symmetry at all. So what you do, you use another technique which is called induction. So you resort to the massive little group. So the massive little group for bosons is SU3, and the massive little group for fermions is SU2. And then you induce all the possible consistent Lorentz representations from the little group. Because if you start from the Lorentz representations, you have equations of motion redundancies. But if you induce it from the little group, you get rid of those redundancies. And this is very similar to what people from on-shell methods they do. And once you induce those characters, you can write them explicitly and then use in the platistic exponential. So we could find the the expression for the characters, both for the Harita-Schwinger field, which is a massive spin 3/2 field, and for a massive spin 2. All of them are singlets. So we take those characters and we concatenate them to the platistic exponentials of the standard model groups, of the standard model fields. Okay. And then after we do that, we can expand the series, and we get to I mean the terms, they are really huge, but I decided to select here only the dimension 6 because it is what could fit in the slide. So for dimension 6 spin 3/2, we have those terms here. And how do we interpret the expansion of the series? So this means that we have, for example, this first term here, it is saying that we have 3 independent operators, which consists of of a B boson, a Higgs, a Harita-Schwinger field, a lepton doublet. Or in the massive spin 2 case, we have 5 independent fields, five independent operators, which consist of 2 B bosons and 2 massive spin 2 particles. So it's very straightforward, the interpretation. To construct the operators from here is much easier than starting from scratch. Okay. And you can also plot the total number of operators as a mass dimension. And we've done that for spin 2 and spin 3/2. And well, a funny thing is that I still don't know how to explain is that the difference in this number also grows exponentially. It is clear why each of them grows exponentially, but why their difference grows exponentially is something that I didn't found yet some explanation, but it's some interesting thing that for sure there's some interesting physics behind it as well. And just to emphasize that this is the counting of operators of the standard model together with an additional singlet, a higher spin singlet, which could be potentially a dark matter candidate. And the very next step after this is to perform phenomenology with those operators. And I think I'm running out of time, but just to conclude, we can there's a systematic way to find operator bases, and this systematic way prevents you from misinterpreting non-physical Wilson coefficients, for example. And the EFTs can serve you as a guide, a true guide to UV completions. And we generalize the formalism to higher spin particles. So the formalism is more applicable to do phenomenology. Okay. So thank you very much for your attention, and yeah, that's it.
Thank you, Bruno. That's a nice presentation. We don't have much time. Maybe one question. No? Okay, let's thank Bruno again. And then we move to Leticia.